Hello. In this part of the lecture, we will look at one of the most widely used technique in modeling, which is called as the linear programming. Linear programming is a mathematical optimization technique and which is used in areas of transportation, production management. So in cases where you have to allocate limited resources for cost minimization or profit maximization or finding the best product mix, you will use this kind of technique. So before we start looking into the details and theory behind linear programming, let's take a look at an example. So suppose that you are managing the production of two types of dog foods. One is bony and one is chewy. Each type of food needs to be processed at two plants before shipping: manufacturing and drying and packaging. The amount of time available in manufacturing plant is 40 hours per week, and in drying and packaging is 35 hours during the week. We are also given that the bony type takes about 50 minutes per ton to manufacture and then 30 minutes per ton for drying and packaging. On the other side, the chewy type takes 24 minutes per ton to manufacture and 33 minutes per ton for drying and packaging. The company must produce at least 20 tons of bony type and 5 tons of chewy type. This could be because they have some orders which they have to deliver on a contract basis. The company's policy is to maximize the production of the combined production for the available time in both the manufacturing and the drying and packaging plants. Your job as a manager is to identify how much of each type of the food should be manufactured. So let's assume that the manager has been managing this facility for a while and he has experience in this area, so he could actually make a good decision based on his prior knowledge. And we can guess that how does producing about 20 tons of bony and 40 tons of chewy type span. So our manufacturing plant will be used for 20 ton multiplied by 50 minutes per ton plus 40 tons multiplied by 24 minutes per ton, which gives us about 1960 minutes, which is less than 40 hours. So that's good. And for drying and packaging, it becomes 20 tons multiplied by 30 minutes plus 40 tons multiplied by 33 minutes, which is about 1920 minutes, which is also less than 35 hours. Of course, in this case, X and Y are greater than 20 and 5 respectively. So our total production becomes about 60 tons. The question though still arises, is this the best? Are we making the most use of our production facilities that are available to us? So how would you answer that question? How about we start raising the numbers? We say, let's go with bony type to be 21 tons and chewy type to be 41 tons. So instead of playing a guessing game or instead of trying to guess a solution, we will fall to a modeling technique called as linear programming. And let's take a look at how will we solve a problem like this using the LP technique. The first step that we will take is formulation, which essentially means we will systematically express the given scenario. In formulation, the first part is to describe the problem, which in this case was actually very well given to us. The second step is we will identify and define the decision variables. So what are the key factors that our decision will identify will be known as the decision variables. Then we will define or determine the constraints. So what are the limitations that we have in our real system that we will have to assure that are followed. And next we will actually define what is called as an objective function. So the objective function is what we will maximize or minimize. Let's take a look at them as we go, and then we will start pointing to these 4 steps in formulation. Let's assume that you produce X tons of bony type and Y tons of chewy type. X and Y are called decision variables. At the end of the modeling, when we have applied our maximization to the objective function, we will get the values of X and Y. So the point to note is that the decision variables are generally the variables for which you need the final answer for, or which are asked of you to be determined using the model. Next, we will look at how do we find the constraints. So we were given that the two plants are available to us for a certain time during the week. And we were also given that it takes a certain amount of time to produce per ton of bony type and certain amount of time to produce for chewy type. So in this case, we were told that 50 minutes per ton for bony type and 24 minutes per ton for chewy type in manufacturing. And same way, we were given that 30 minutes per ton for drying and packaging of bony type and 33 minutes for drying and packaging of chewy type. So what we did is we said, okay, 50x plus 24y should be less than 2400. So what we've done is we have converted 40 hours into minutes, so the units are same on both the sides. And similarly, for drying and packaging plant, 30x plus 33y should be less than 2100. Again, we've converted 35 hours into minutes by multiplying it by 60. And also in the question we were given that you have to produce a certain minimum amount of each. And we was told that X, which is the bony type, should be greater than 20 tons and Y should be greater than 5 tons. So here it is. Based on the problem that was defined, we have now identified 4 limitations or 4 restrictions which are set in the real system, and we are using those in our model. These are termed as constraints. So depending on the problem, there could be different number of constraints. They all depend on what the real system has limitations. And finally, we come to the objective function. The question asks us that the management wants to maximize the total production. So the total production in this case will be amount of bony type produced plus amount of chewy type produced. So we define our objective function z as z is equal to x plus y. So our goal is maximize. LP can be used to minimize as well. So collectively, the formulation gave us maximize z is equal to x plus y, which is called our objective function, and the 4 constraints which you see on the screen. The last step is we will find the solution, and for now we will use what is called as the graphical method. Based on the constraints that we had found from the formulation, we will start plotting each of those constraints onto an xy plane, where x in this case is the amount of production for bony type and y is the amount of production for chewy type. I have picked up the first constraint, which was 50x plus 24y. I have replaced the inequality sign less than equal to with equal to sign, and then I have moved everything except the y on the right side. So my slope intercept form looks what you see on the screen right now. And I can actually find the intercepts of x and y by substituting x and y as zeros and then plot the line. So our line will be joining the points 0, 100 and 48, 0. The 2 blue color arrows that you're seeing are taking care of the inequality sign. So according to this constraint, the area that we are interested in is pointing towards the arrow. Anything on the right side of the red line is not falling within our constraint. Anything on the left side of the line parallel to the blue arrows is falling within our constraints. So on this slide you see that I have plotted the second, the third and the fourth constraint as well. Next, I have started adding the arrow directions. So after we have added directions to take care of the inequalities, the area which is colored orange shows the area which is feasible, fulfills all the constraints. This area is appropriately named as the feasible region. What it means to us is that the answer that we will get for x and y should lie within this region. And now we have to identify which values of x and y give us the maximum value for the objective function. We'll introduce another fact that the maximum or the minimum value of the objective function, in this case it is z is equal to x plus y, will fall on one of the corner point feasible solution. What it means is that the value which is of x and y here at point 1, point 2, point 3 or point 4, one of these set of coordinates will satisfy the maximize condition, and at the same time another one of them will satisfy the minimize condition. So now, of course, the next task for us becomes how do we identify these coordinates, and we'll use simple algebra. If we want to find the coordinate of point of intersection 1, which is between the line blue and the line brown, will be, then we have to solve the linear equations with constraint 2 and constraint 3. Similarly, for finding the intersection point 2, which is between red and blue, we will find the solution of equations from constraint 2 and constraint 1. Next, for point 3 will be between the red and the yellow line, which means constraint 1 and constraint 4. And intersection point 4 is between the brown and the yellow line, which is between constraint 3 and constraint 4. So doing that, we will see that the point 1 has coordinate 20 and 45.46, and if we substitute these values in the function, it becomes 65.46. And similarly, we find the coordinates of point 2, 3 and 4. We can see clearly that our objective function is has a maximum value of 66.45 tons, and that happens if we produce 30.97 tons of quantity X and 35.48 tons of quantity Y, in this case bony type and chewy type.